We have learned that power electronic converters are used to interface sources and loads operating at different voltage levels. These voltage levels could be AC or DC. There will also be AC or DC currents corresponding to the voltages as we are talking about electrical circuits. How do we visualize these voltages or currents? We visualize them as waveforms. A waveform is typically a representation of the variations in a physical quantity against time. The following discussion focuses on voltage waveforms, and the same can be applied to currents as well. We know that AC voltage is a time varying sinusoidal voltage and DC voltage is a constant voltage which doesn't vary with time. Here are the waveforms of AC and DC voltages that are known to us. So when we try to visualize AC voltage, this is what comes to our mind. So when we try to visualize DC voltage, the waveform of DC voltage, this is what comes to our mind. This ideal DC, ideal AC. Let us call this peak magnitude of AC voltage as Vm, and this is minus Vm. What can we say about the ideal AC waveform? It is a sinusoidal function of time. Its magnitude has both positive and negative values, and the positive and negative values span over equal intervals within one full cycle of the AC waveform. In other words, the area under the positive part of the waveform and that under the negative part are equal, which means that the AC waveform has zero average value. How about the ideal DC waveform? Its magnitude doesn't vary with time and is always constant, and the magnitude can have either positive or negative value. For example, you can have a DC voltage like this also. But in power electronic circuits, the waveforms of AC and DC voltages or currents don't look exactly the same as the ideal AC and DC waveforms because of the circuit elements involved. So we need to have a more generic way of distinguishing the AC and DC waveforms. Here is how we distinguish. A waveform having zero average value is considered as an AC waveform, while that having a non-zero average value is considered as a DC waveform. Zero average value and non-zero average value. Let us try to understand this with a few examples. The AC waveform in a power electronic circuit could look like a square wave. So it is periodic, it has both positive and negative values and a zero average value, but it is not sinusoidal. A few other AC waveforms that are encountered in power electronic circuits are the trapezoidal waveform, being shown in red color, and then we have quasi-square waveform, and all these are functions of time. And there can even be other types of AC waveforms. One can have a waveform like this, or we can even look at a waveform with multiple steps. These 5 waveforms are a few examples of AC waveforms that we come across in power electronic circuits. What is the common feature of all these waveforms? They have zero average value. Now let us try to look at a few DC waveforms. The DC waveforms can have only positive values, only negative values, or both, but its average value should be non-zero. So here is an example of a DC waveform. So it has all positive values and it has a finite average value, positive average value. There is yet another example of a DC waveform. You can have this variation, a smaller variation. It doesn't come all the way to 0. It will have a positive average value. Then we can have an example of a DC waveform with both positive and negative values. For example, you can look at a waveform like this. So this has a positive average value because the positive cycles have, the positive part has more area than the negative part. So here is yet another example of a DC waveform. It also has a finite positive average value, but the variation looks like a triangular waveform. The DC waveforms could also have negative average value. For example, you can have some waveform like this. So which has a negative average value. All these waveforms are functions of time. Consider two DC waveforms. For example, you consider this blue color waveform and this green color waveform. Blue and green colored DC waveforms. Which of these represents DC better? The one which is closer to the ideal case, that is, the one with less variation in magnitude, is a better DC waveform. Consider two AC waveforms now. For example, you can consider this blue and red. So the one which is closer to a sinusoid is a better AC waveform. There are methods to quantify whether a given waveform is close to the ideal DC or the ideal AC waveform. We shall learn about these methods of quantification shortly.